Imagine trying to query a database that holds 1 trillion rows of data.
Right, which is just an unfathomable amount.
Literally petabytes of information. And the catch is you need your answer in less than a single second.
Yeah, for most data engineers listening, that sounds like a physical impossibility. I mean, with traditional data processing, hitting enter on a query that massive means you're going to be staring at a loading bar for hours.
Or days, even.
Exactly, in some cases days. The system simply has too much ground to cover on the fly.
But today we are unpacking how a tool called Apache Kylin pulls off this seemingly impossible magic trick. Welcome to today's deep dive, where our mission is to break down the architecture, the history, and the capabilities of Kylin, which is this open-source distributed analytics engine.
It's a really fascinating piece of tech.
Yeah, we want to figure out where this tool came from, how it actually operates under the hood, and, how you can decide if it belongs in your own massive data projects.
Because to really appreciate how Kylin manages sub-second query latency on petabytes of data, just looking at the code isn't enough.
Yeah.
You really have to look at the pressure cooker environment that forced it into existence.
Right.
In the world of big data, necessity isn't just the mother of invention, it's the mother of extreme optimization.
So let's wind the clock back to 2013 to see that pressure cooker in action. We are in the R&D department of eBay in Shanghai, China. Think about eBay's scale back then.
Just billions of transactions.
Billions. You have every click, every bid, every final purchase across every single country they operate in.
And eBay's internal analysts, they needed to perform interactive analysis on that data set. And interactive is the key word there.
Meaning they couldn't just run a batch job overnight.
Exactly. They wanted to ask a question, see the result, tweak a parameter, and get a new result instantly. They needed to move at the speed of thought to actually make business decisions.
But running a simple SQL query on a database that large creates this massive physical bottleneck. I mean, if you ask a traditional database to find, say, the total sales of electronics in Germany for a specific Tuesday in 2012.
Right, a super specific slice of data.
The system literally has to scan billions of records on the fly to tally that up. You run the query, you go grab a coffee, you come back, and the disk is still just spinning. It's totally I/O bound.
Because reading from a disk, even a really fast one, it takes time. When you multiply that time by billions of rows, the math just fundamentally doesn't work for interactive speeds.
It's like querying a traditional database of that size is like walking into a warehouse the size of Chicago and being asked to find a single receipt from 5 years ago.
Right. Good luck with that.
Yeah, it doesn't matter how fast you walk, it's going to take forever. So eBay's engineers realized they couldn't just walk faster. They needed a complete paradigm shift.
And that shift was pre-computation.
Right. They built a solution that is essentially like having an army of assistants who have already sorted, tallied, and summarized every possible receipt combination before you even walk through the warehouse doors. They called it Kylin OLA and open sourced it on GitHub in October 2014.
And the broader tech community's reaction was pretty immediate. I mean, by November 2014, it was adopted into the Apache Software Foundation Incubator.
Wow, that's fast.
Yeah, and by December 2015, it graduated to a top-level project. In the open source world, that kind of trajectory is blindingly fast.
It really highlights how desperate massive organizations were for this specific fix. We saw massive adoption by companies dealing with just unbelievable scale. JD.com, Meituan, Xiaomi, Yahoo Japan, and a bunch of heavily regulated telecom and financial institutions.
Because they all had the exact same warehouse problem.
But I want to pause here for a second because the claim of sub-second queries on petabytes, it still sounds a little bit like marketing speak. How does it physically do it? If traditional databases are failing because they have to scan billions of records on the fly, what is Kylin's actual bypass?
So the core theoretical concept is pre-computation. Essentially, Kylin trades storage space for speed. It uses a mechanism called multidimensional OLAP cubes, and OLAP stands for Online Analytical Processing.
Okay, the famous OLAP cube. If you're listening and you haven't dealt directly with data warehousing, the word cube sounds incredibly abstract. So let's ground this a bit. How does this cube actually function?
Think about how your data is naturally organized. Usually it's in a star or snowflake schema. So picture a star. In the center, you have a massive fact table.
For instance, a raw list of every single sales transaction.
Right. And radiating outward from that center are your dimension tables.
So the dimensions are the categories, or I guess the perspectives you want to slice the data by. Things like the time of the sale, the geographic region, or the product category.
That's exactly it. And then you have your measures. Measures are the actual numerical values you want to calculate based on those dimensions. So
Mhm.
total sales in dollars, the average price of an item, the total count of items sold, things like that.
Okay, I'm following.
What Kylin does is it looks at those dimensions and measures, and it pre-calculates the answers to the different combinations you might want to ask about later.
So it's literally doing the math beforehand. It takes the electronics dimension and the Germany dimension and the Tuesday dimension, calculates the total sales measure, and saves that specific answer.
Yes. It builds these out as aggregate indexes and table indexes. So an aggregate index stores those rolled up summaries, like the total revenue by product and by month.
Okay.
And a table index stores the underlying details, so you can still do drill down queries. Like if you want to view the last 50 specific orders from that region, you can do that without having to go all the way back to the raw source data.
So when you eventually sit down at your dashboard and you hit enter on your SQL query, Kylin isn't scanning the raw data at all.
Zero raw data scanning. It intercepts the query, figures out which pre-calculated index contains the answer, and just fetches it.
Wow.
Yeah, that is the secret to the milliseconds response time on a trillion rows. The
Okay.
heavy lifting wasn't done when you hit enter. It was done 12 hours ago.
Well, let me stop you there, because if I'm listening to this and mapping out my own data architecture, I'm doing the math on those combinations. If you are pre-calculating literally every possible combination of your data, every region against every product against every hour of the day, doesn't that create a huge combinatorial explosion?
Oh, absolutely.
Aren't we talking about an absurd amount of storage space and upfront computational power to build this thing?
You've hit on the central tension of using Apache Kylin right there. The build process, which the documentation refers to as cubing, is incredibly resource intensive.
I would imagine.
Yeah, you are eating up huge amounts of compute power and storage to generate these indexes. In fact, the cube can sometimes be larger than the raw data itself.
See, that sounds like a terrible trade-off. Why would I want my summarized data to be physically larger than my raw data?
Because you have to look at the economics of enterprise businesses. Compute time during the night, when the servers are otherwise mostly idle, is cheap. Human wait time during the day is incredibly expensive.
That makes sense.
Right. If you have a team of highly paid data analysts or a CEO waiting on a dashboard to make $1 million decision, you cannot afford for them to wait 10 minutes every single time they adjust a filter.
You let the servers sweat at 2 in the morning so the business user doesn't have to wait at 9 in the morning.
Precisely. And that economic reality is what drives Kylin's entire architecture. Because to pre-compute data on that massive scale, you need a highly specialized, highly optimized engine. You can't just run this on a standard SQL server.
Let's get under the hood then. The technical breakdowns, especially the Bildung tutorial, they divide Kylin's architecture into several modular components. And crucially, it's built on top of the Hadoop ecosystem. It doesn't actually try to store the data itself. It sits on top of massive distributed systems like HDFS, Hive, and Spark.
Which is really smart because it leverages existing big data infrastructure rather than reinventing the wheel.
Right. So to help you visualize how these components talk to each other, let's go back to our analogy. But instead of a warehouse, think of Kylin's architecture like a massive high-end restaurant operation.
I like this. Let's trace a query through this restaurant. Where does the user start?
So the entry point is the REST server. It receives the user or API requests. In our restaurant, the REST server is the waiter. You give them your order, which in this case is your standard SQL query, and they take it to the back.
And the waiter hands that ticket to the query engine. Think of the query engine as the expediter in the kitchen. In Kylin, this engine relies heavily on a framework called Apache Kylin to parse your SQL queries and generate an execution plan.
Wait, if the answers are already pre-calculated, what is Kylin actually doing? Why do we need an execution plan to just fetch a saved answer?
Because the user is just writing standard SQL. They might write a really complex query with all sorts of joins and filters. Kylin is the smart expediter who looks at this complex ticket and realizes, hey, I don't need to send this whole complicated order to the kitchen.
Ah, it knows the prep cook's already made it.
Exactly. It says the prep cooks already made this exact sauce combination an hour ago. I just need to route this request to shelf number 4. Kylin finds the absolute shortest path to the pre-computed answer. And a huge benefit here is that Kylin supports standard ANSI SQL.
Meaning your analysts don't have to learn some proprietary Kylin query language. They can use the SQL they already know, or just plug in a tool like Tableau and it just works out of the box.
Right, so Kylin routes the query. But who actually prepared all that food before the restaurant opened?
That is the job engine. The job engine is the team of prep cooks who came in at 4 in the morning. Their job is to generate and execute the massive distributed computing jobs that build the raw data into those OLAP cubes. And historically, this used MapReduce or Apache Spark.
And just for context, MapReduce and Spark are engines that take a massive task, like summarizing a billion rows, and they chop it up into thousands of tiny parallel tasks spread across a whole cluster of machines.
So they did all the heavy lifting, the chopping, the reducing, long before the first customer even walked in.
Exactly.
Which brings up a logistical question. If the prep cooks did all this work at 4 a.m., where is all that pre-calculated data sitting so it doesn't spoil before the dinner rush?
That would be the storage engine. In the original architecture, this was primarily Apache HBase, which is a distributed, scalable, big data store. More recently, it has evolved to support columnar storage formats like Apache Parquet.
So the storage engine is the walk-in fridge.
Yep, the walk-in fridge. All those pre-computed cubes are perfectly organized in there. When Calcite, our expediter, asks for the data, the storage engine just grabs the specific container and hands it over.
And wrapping all of this together is the metadata management system. This is the persistent storage for the cube definitions, the routing rules, and the job statuses. It's essentially the master recipe book and the kitchen schedule rolled into one, ensuring the expediter, the prep cooks, and the waiters all know exactly what is going on at any given time.
It's a brilliant, highly extensible architecture. But it's also important to recognize that technology never stops moving. That original architecture from 2014 was heavily reliant on traditional Hadoop, and it required a lot of manual, painstaking cube design by data engineers.
Right. The sources make it very clear that Kylin hasn't just stayed stuck in 2015. Big data has fundamentally shifted away from those old on-premise Hadoop clusters toward cloud-native object storage and modern data lakehouses. Let's talk about how the system evolved into Kylin 5.0 to keep up with that massive shift.
Version 5.0 introduces some really radical upgrades. First off, they introduced internal tables. This is a move away from the rigidity of a pure cube-only architecture.
Okay, how so?
Well, internal tables are designed for much more flexible queries and modern lakehouse scenarios. It allows Kylin to act more like a traditional data warehouse when it needs to, without sacrificing the cube speeds for the really heavy workloads.
And speaking of speed, the technical breakdown from Byte Explorer highlights something called the native compute engine. In version 5.0, they integrated a backend called Gluten ClickHouse.
Yeah, that's a big one.
The Bale Dung tutorial notes this brings a 2 to 4 times performance improvement over using vanilla Apache Spark. But, gluten sounds like baking, and ClickHouse sounds like a marketing agency. What is actually happening at a technical level here to double or quadruple the speed?
It really comes down to how machines process data at a low level. Historically, tools like Spark run on the Java Virtual Machine, the JVM. And the JVM is great, but it processes data row by row, and it has overhead from things like garbage collection. ClickHouse, on the other hand, is built in C++ and uses something called vectorized execution.
Vectorized execution, meaning instead of processing one row at a time, it processes data in large blocks or columns all at once?
Yes, exactly. It leverages the actual hardware of modern CPUs, specifically SIMD instructions.
Which is single instruction, multiple data, right?
Spot on. It uses SIMD to perform the same operation on multiple data points simultaneously. Gluten is basically the bridge that allows Kylin to offload its compute tasks to this blazing fast ClickHouse engine. You're essentially swapping out a strong human prep cook for an industrial food processor.
Okay, that makes total sense for processing historical data. But one of the historic criticisms of OLAP cubes is that they are inherently backward-looking. If you build the cube overnight, your data is always at least a day old. In a modern enterprise, yesterday's data might as well be ancient history.
Yeah, that was a massive limitation for a long time. But Kylin 5.0 addresses this head-on with streaming batch fusion. It now fully supports Apache Kafka, which is a distributed event streaming platform.
But wait, how does a system built entirely on pre-computation handle live streaming data? You can't pre-compute something that happened 3 seconds ago.
You can't. It handles it by doing both simultaneously and fusing the results.
Oh, wow.
Yeah, so when you query Kylin 5.0 now, it grabs the heavy historical context from the pre-calculated batch cube, and in parallel, it queries the lightweight real-time data streaming in from Kafka and it just pulls them together seamlessly in memory.
So you get the instant historical baseline fused with what happened 5 seconds ago.
Exactly.
That is incredibly powerful. But the feature in version 5.0 that really caught my eye is the model and index recommendation. The Apache documentation details how the engine can analyze your query history and automatically optimize indexes and recommend models. Is this the end of the data engineer having to manually design these cubes?
It's certainly the end of cubing as a sort of dark art. I mean, in the past, designing an OLAP cube required incredibly deep domain knowledge. If an engineer made a cube too broad and included every single dimension, the build time would take 3 days and crash the servers.
And if they made it too narrow?
The business user would run a query on Tuesday, and the cube just wouldn't have the answer.
So you were constantly just guessing what the CEO might ask tomorrow.
Exactly. It was a guessing game. The auto-modeling recommendation engine changes the paradigm entirely. It watches what queries are actually being executed in the real world. It identifies patterns. Then it recommends or automatically tailors the indexes to match reality, rather than matching an engineer's best guess. It lowers the barrier to entry significantly.
That is a massive operational shift. But with all these powerful features, sub-second queries, streaming fusion, auto-modeling, it's really tempting to look at Kylin and say, this is magic, let's use it for absolutely everything.
Oh, for sure. But no software is a silver bullet.
Exactly. So if you're listening and wondering when you should actually deploy this in your own stack, let's look at the best practices. When does Kylin shine, and when is it the completely wrong tool for the job?
It's all about workload matching. Kylin is purpose-built for read-heavy workloads where query speed is the absolute highest priority. If you are building mission-critical business intelligence dashboards, say you are hooking up Tableau, Power BI, or Apache Superset for your executive team, Kylin is practically peerless.
The Databricks post specifically highlights use cases like telecom network monitoring and real-time fraud detection. In banking, if someone swipes a credit card, you can't wait 5 minutes to figure out if that transaction fits a fraudulent pattern based on their 10-year history. You need to bounce that live swipe against massive historical models instantly. That's a perfect use case.
Yes, exactly. But where you absolutely do not want to use Kylin is for ad hoc exploratory queries.
Define ad hoc in this context, just so we're clear.
Ad hoc means you don't know the question until you ask it. If you are a data scientist going on a fishing expedition in the data, looking for weird anomalies across random, unindexed columns to see if there's a correlation you've never thought of before.
Because if you've never thought of it, Kylin hasn't pre-computed it.
Right. If the prep cooks didn't prep it, you can't order it. If you try to force Kylin to do ad hoc exploration, it has to bypass the cube and push the query down to the underlying raw storage anyway, which completely defeats the entire purpose and gives you terrible performance.
So if you are building a dashboard that the CEO checks every morning at 8 a.m. and expects to load instantly, Kylin is your best friend. But if you're a data scientist hunting for unknown patterns, you want to look elsewhere, maybe to engines like Presto or Apache Druid, which are optimized for flexible ad hoc exploration on the fly.
Totally. And if you do decide Kylin is the right fit, the sources are very clear on a few critical best practices. First, even with auto-modeling assisting you, you have to be super vigilant about avoiding overly wide cubes.
This goes back to the combinatorial explosion we talked about earlier.
Exactly. If you have a table with 100 columns and you try to make every single one a dimension in a single cube, the number of possible combinations grows exponentially. Your build times will explode from hours to days, and you'll waste petabytes of storage on combinations no one will ever actually query.
The documentation also stresses the importance of partition pruning. Can you briefly explain how that helps?
Partitioning basically means dividing your data logically, usually by time, like grouping data by day or month. When you write a query for just this month's data, partition pruning allows the query engine to completely ignore all the historical partitions.
Oh, I see.
It skips the irrelevant data segments, which drastically cuts down on the data it has to scan, further improving those millisecond response times.
And finally, automation is non-negotiable. The Baildome tutorial emphasizes that you shouldn't be triggering these cube builds manually. You really need to use Kylin's REST APIs to integrate the build process into your CI/CD pipelines or automated cron jobs. You want this running seamlessly in the background during off hours.
Yeah, if you orchestrate it correctly, the end business user never sees the immense complexity happening behind the scenes. They just log in, filter a petabyte of data, and experience magic speed.
Let's pull all these threads together. We started with a massive physical bottleneck at eBay in 2013. Basically, the sheer inability of traditional databases to scan billions of rows for interactive analytics. The solution was Apache Kylin, an OLAP engine that turns the problem on its head. It trades upfront storage space and off-hours compute resources in exchange for sub-second query speeds during the day, achieving this by pre-computing data into multi-dimensional cubes.
And we looked at how its modular architecture routes user queries through Apache Kylsite to fetch these pre-computed answers from storage engines like HBase or Parquet, completely avoiding raw data scans.
And we saw how the system hasn't stood still. It evolved into Kylin 5.0, stepping into the modern lakehouse era with internal tables, boosting processing speeds with the vectorized gluten ClickHouse engine, and tackling real-time data by fusing historical batches with live Kafka streams.
And perhaps most importantly, we explored how it lowers the barrier to entry with auto-modeling, actually learning from user queries to optimize the cubes automatically.
Which leaves me with a final thought for you to ponder. We talked about our warehouse analogy earlier, the army of assistants prepping all the data before you even arrive. Well, if Kylin 5.0 is now automatically analyzing query histories to build and optimize these data cubes without human intervention, we are kind of approaching a reality where the army of assistants is entirely self-managing.
It's a wild thought.
It is. If algorithms can observe business behavior and automatically structure the data architecture to match it perfectly, what does that actually mean for the traditional role of the database architect? Are we looking at a future where optimizing data models is no longer a human job at all? It's definitely something to think about the next time your dashboard loads in a millisecond.